Okay, here we go. Nothing to it but to do it. Last day, we introduced chi-squared tests. A couple of nice things about chi-squared tests is that we're only doing hypothesis testing. The conditions that we have to check are a little bit simpler, although they're different, but simpler, right? And so that's nice. All right, we started and we nearly finished this question here, comparing how people are accessing the textbook for a course. And so we had 3 categories and we were just working through, it was kind of holding our hand through a hypothesis test with a chi-squared test statistic. Yeah. I know it doesn't feel like it right now, but your formula sheet gives you everything that you need to know. Okay, besides the conditions, right? I don't have the conditions on there. Those are for you to memorize, but the null hypothesis I give you, and it's the observed distribution equals, I guess, the expected distribution for goodness of fit testing, right? Do the observed counts line up with what you were expecting, or are they significantly different, right? And so the alternative is that the observed distribution does not equal the expected distribution. Okay. We said, okay, how do we calculate the chi-squared test statistic? We take the observed minus the expected, so the distance between the two, right? And then we square them, and then we divide by the expected count for each cell, and then we add them all up. Okay. And then to use the chi-squared table, because that's all we have for the quiz, right? You can use software, obviously, but not on the quiz, you won't have it. Then we need the degrees of freedom, which is going to be the number of categories minus 1. Okay. And so we went through and we stated the null and the alternative hypotheses. We talked about how do we calculate the expected values, right? And so we had some proportions in each category, right? And then we can multiply that by the total, which means that the expected total should be the same as the actual total, right? So you're going to keep all the decimals for your expected values, otherwise it's going to make a mess. The assumptions for a chi-squared test, like I said, are relatively simple. We have to assume independence. So assume that each of these counts that make up the table are independent of each other, right? Which we can achieve by random sampling, or we just have to assume it. And then there's the sample size condition that all expected counts are greater than 5. Okay? And then once those two are satisfied, then we can use the chi-square test. So relatively approachable in that sense. Okay, so then we calculated the chi-squared test statistic, right? And I used Desmos just for some simplicity here. But if I was working on paper, I'd probably have my observed counts in one column and then the expected counts in another column. And I would build this all out, kind of adding columns as I go, right? The observed minus the expected, and then make a new column where you square it maybe, and then make a new column where you divide each of those values by the expected value, right? And then add those all up. So you just kind of build it out slowly. I promise there will be 3 categories. Okay? No more, no less, can't do less. Then what should you do? 2 sample proportion test, right? And so we can't do less than 3, but I promise I won't do more than 3. It will be 3. Okay? Otherwise, this calculation gets way out of hand, right? You can do it, but hey, what does that mean? If I just told you that there will be 3 categories, then your degrees of freedom will be 2, right? For the goodness of fit test. Oh, and that's where we That's where we got to. So let me just pick up there. And I think I said something cute like, oh, just finish this on your own time and then we'll pick up where we left off next day. So cute. Okay. So continuing from last day. We calculated our chi-squared test statistic, and let's see if there was another part that I should be tackling here yet. Oh yeah, calculate the chi-squared test statistic, the degrees of freedom associated with it, and the p-value. So now we need to find the p-value, and maybe I'll grab this, copy. Okay. So now we need to find the p-value. So for the p-value, we need the chi-squared table. Okay. I'm just gonna grab the first 3 degrees of freedom because I already know that I have 2 degrees of freedom, so I don't need any more of this table. So we have 2 degrees of freedom. Right. And now for our p-value, right? The p-value is what we're gonna find here. So now at 2 degrees of freedom, what are we gonna do? Well, I can take this chi-squared test statistic 2.32, very small, right? Even at 2 degrees of freedom. So here 2.32 would go here, right? Same as what we've been doing before, right? When we use the Z table, the shape of the chi-squared distribution is skewed, but the idea stays the same, right? And so here is a chi-squared of 0, and we have a calculated chi-squared 2.32. Okay. The table starts at 2.41. And the area in the tail, remember the chi-squared, because it's skewed, the p-value is just the area in the upper tail, right? And so that's why the table just gives you the upper tail area is 0.30. Okay. Which means what? It means, well, our p-value is greater than 0.3, right? Because I have more area in the upper tail than 0.3, but without an upper limit on the upper tail area, I have to go to 1, right? The maximum it can be is 1, so it's somewhere between 0.3 and 1, right? And so here, this area is 1.00, right? And so here, a chi-squared of 0 has an area of 1, 1, 1, regardless of the degrees of freedom, right? The area in the upper tail is just 1. Okay. Oh, I did those backwards. I feel like I could tell I did them backwards because I got a look. Wait, that doesn't make sense. Here, an area of 1 is when chi-squared is 0, 0, 0. There. That makes more sense. All right. So then the p-value And for chi-squareds, we don't worry about one-sided or two-sided p-values, right? Because it either fits the distribution or it doesn't, right? So the p-value is between, and maybe I'll do it properly down here. So since the calculated chi-squared is equal to 2.32 is between 0 and 2.41. There. Oops. Then the p-value is between 0.30 and 1.00. Nice. Wait. Hey, these are all from last day. All right. Okay. We also talked about the critical value approach, right? So it asks for the p-value, and we know how to work with the p-value, or relatively comfortable with the p-value, right? And if the p-value is one of those things where you're like, I know I'm supposed to know what it is, but I'm still not getting it, it's okay. It's gonna come. It will come to you. But just go through the motions and eventually it will click. So we said we could use the critical value approach. So it's not asking for it, but it's good to practice, right? And so, or we could use the critical value approach. I think we have to skip to, it didn't say what alpha level to use, but I'll grab this next part while I'm here. So if it doesn't tell us what critical value or what alpha level to use, just default 0.05 still. Okay, that's always going to be your default. Okay, so use the default alpha equal to 0.05. Okay. So then what we get, and let me just plunk this down here before I forget. So then what we have from the table, chi-squared table, copy. We could say, okay, well, I can just look at the chi-squared table instead and force the area in the tail to be 0.05, right? Then that's going to tell me what chi-squared has to be bigger than in order for me to reject H naught, right? And so here at 2 degrees of freedom, right, still. And so the chi-squared, chi-squared critical, so crit is 5.99. Okay. In terms of this number line, right, what it's saying is, okay, 5.99 has an area in the tail of 0.05. So my chi-squared, my calculated chi-squared then has to be larger than 5.99 in order for me to reject H naught, because that's how I get an area in the tail less than 0.05, right? So they're definitely linked, okay? And you can use this for z-scores as well. We just didn't. I saved it for now until we were kind of comfortable with the p-value approach, which is the more classical approach. And especially in papers and stuff like that, if you're reading kind of academic articles, they'll use the p-value approach. So, right, but the same conclusion, right? My calculated test statistic, so my calculated chi-squared is not less than the critical value. Therefore, the area in the tail is not less than 0.05. So my p-value is not less than 0.05, which means I do not have enough evidence to reject H naught. Right? So it doesn't matter which approach I use, I'll land in the same place. Wait. So based on the p-value calculated in part D, what's the conclusion of the hypothesis test? Interpret your conclusion in this context. We shouldn't have to say that, right? If I ask you for a conclusion, you should probably do all the parts, right? There's 3 parts. Compare your p-value to your alpha level, then tell me what that means in terms of H naught, right? And then what does it mean in terms of the question? So this is basically your step 4 of your hypothesis test, which is your conclusion. Since the p-value is between, and I'm just going to say what it is between 0.3 and 1, 1.00. I don't know. I just like to have some 1.30. How about that? 2 decimal places. Snazzy. Since the p-value is between 0.3 and 1, it is not less than the alpha level, right? And because I'm assuming it's 0.05, this is overkill, but usually I just say the assumed alpha level of 0.05. Okay, so it is not less than the assumed alpha level of 0.05, which means we do not have enough evidence to reject H naught. Enough evidence to reject H naught. If I'm not rejecting it, right, then you don't have to say the in favor of HA because you're not rejecting H naught. Which means, therefore, the observed distribution of, now let me, oh, I don't have it. Let's see here. Where's our null hypothesis here? So I don't have enough evidence to reject this. So this is my conclusion. The observed distribution of textbook formats equals the professor's predicted distribution of textbook formats, right? Or is not significantly different from the predicted distribution or something like that. Therefore, the observed distribution of textbook formats is equal to the predicted distribution. Or maybe I'll say the distribution the professor predicted. Distribution the professor predicted. Since we have the quiz tomorrow, I want to highlight that your conclusion is worth 3 marks. Usually a hypothesis testing question, excluding the assumptions, I make it out of 7 marks. Okay, and so 4 for the rest, right? P-value is 1 mark, calculating your test statistic is 1 mark, and your hypothesis, because it's so important, is 2 marks. right? And so usually there's some freebie marks in there that are kind of unaccounted for. But that's just how I set it up. So 3 marks for your conclusion out of 7 is a good chunk, right? And so each one of these parts is going to be 1 mark each, right? So since the p-value is between 0.3 and 1, right, compare, it's not less than the assumed alpha level of 0.05, right? So that's your first mark. So part 1 is compare the p-value to the alpha level. All right. That's your first part of your conclusion. Second part of your conclusion, what does that mean in terms of H naught? Do you have enough evidence to reject H naught, or do you not have enough evidence to reject H naught? Those are your only options, 2 options. So your conclusion in terms of H naught. And then the one that people love to forget, because you've done all this work and you're exhausted, is what does that mean in terms of the question, right? So the conclusion in terms of the question. Conclusion in terms of the question. How far? Okay. So each one of those is a mark. Okay. And ideally, I want you to tell me what the p-value is, right? Because often that's where you catch yourself, right? If you tell me that 0.15 is less than 0.05, but so I can't give you a mark there, but then if you follow through and you told me that it's less than 0.05 and you tell me that I have enough evidence to reject H naught, that's fine. I'm happy with that, right? Because you have to follow through with what you said, right? But usually I see these kind of switch back and forths where you lose a lot of marks, right? So you want to be super careful. But as long as your logic follows through, even if you do something weird, right, just stick with the logic and you'll be fine. Right? Even typos and stuff like that, I usually take half the mark off for a typo, but then if you follow through, I'm happy, right? Then I'm not gonna penalize you anymore. Okay, so I want to, I guess that's not really the end of the review, but it's the end of stuff from last days. So kind of review, I guess. I should write it down. So, but kind of weird to put it here. The quiz 3 information, I think I said it on Tuesday, but I'm not sure I wrote it down. So there will be 4 questions, right? A 1 sample proportion, a 2 sample proportion question that you have to do, okay? And then you're gonna have a choice between 1 of 2 chi-square tests. So we've only seen 1, so you should be relatively comfortable with a goodness of fit test, but I will add the test of independence, which we're about to cover. It'll be easier to do, but it'll be new. So you get to choose which one you want me to mark. You have to tell me which type of question each of them are for 1 mark each. And then so the one that you don't do is just 1 mark, right? You tell me which type, and then I just mark 1 of the chi-squareds. You're welcome to try them both and then decide which one you want me to mark, and you'll have to tell me which one you want me to mark. Right, so you'll have the option. Should I write that down here? It's kind of a weird spot. Anyways, quiz number 3. As a note, you can check out assignments 11, 12, 13, and 14 for more practice. I also posted that practice for quiz 3. It's kind of a big one, but it's practice for the quiz. I realized I forgot to put type 1 and type 2 errors on there. Oh well. Test it on the final. So there's going to be 4 questions. State the type for each, right? 1 mark each. And then do, you have to do a 1 sample proportion question. Hey, I did write it down. It's all coming back to me now, right? Confidence interval, hypothesis test, or sample size calculation are your options, right? It's not going to be both confidence interval and hypothesis testing, but those are the options. 2 sample proportion question, either a confidence interval or a hypothesis testing question. And then 3 is one of a chi-squared goodness of fit or a chi-squared test of independence. Okay. Which leads me to section 6.4. Chi-squared test of independence. A test of independence is when we have a 2-way table, which means that we have 2 categorical variables, right? And so a test of independence is for 2 categorical variables, which might look something like this, right? And so you have variable number 1 with category 1, category 2, and category 3, for example. And then you have variable number 2 with category 1, category 2, and category 3, and maybe let's make a category 4. Let's get wild. Okay. So 2 categorical variables are usually summarized in this 2-way table, right? This is called a 2-way table. Right, because it's got two variables. Okay. Whereas the goodness of fit test, if you were to summarize the information for a goodness of fit test, it would be in a 1-way table, right? And so you have your categories here and you have your counts for each of those categories, but there's no second variable, right? So one kind of obvious way to see it, if I'm nice enough to put things in a table, right, then you'll be able to see, okay, well, I've got categories for 1 variable, making a 1-way table, then it's a goodness of fit test. That's my only option that we've introduced. There are others kind of outside this classroom, but still. Whereas if you have a 2-way table, then you're going to do a test of independence, right? Is variable 1 independent of variable 2? And which one is which, it doesn't really matter. Okay? And so I want to bring this one in because I think it does a really nice job of just summarizing 1-way tables versus 2-way tables if what I said doesn't make sense, which is fair. A one-way table describes counts for each outcome in a single variable, right? So that's a one-way table. And a two-way table describes counts for combinations of outcomes for two variables, right? When we consider a two-way table, we often would like to know, are these variables related in any way? Which is, are they dependent or are they independent of each other? Okay, nice. So now, if we have a look at the formula sheet, right, moving down here, so we did the chi-squared goodness of fit testing, and now I think we've kind of matured enough to introduce the formula sheet right away. And if you had to, if you absolutely had to, I feel confident that you would be able to solve a test of independence question with just this information. Okay, I'm not going to make you do that. Well, sort of on the quiz tomorrow, but you don't have to, right? You can if you want to, right? But that's where we want to get to, is I just give you this key information, and if I tell you, hey, this is a chi-squared test of independence, then you're kind of able to cobble something together. But Emily, I want to be more confident than that. Just cobbling things together, that doesn't sound that fun. But that's where we start, right? So the only kind of scary thing here is the expected counts, right? Before, we had some idea of the distribution that I want to compare it to, right? Now the expected counts are going to come from the row and the column totals and the grand total of the table itself, right? And so that's kind of fun in a way. But let's recap. So let's note the conditions are the same as for the other chi-squared test. The conditions are the same for both chi-squared tests. And I think it's any chi-squared test. So there are other chi-squared tests that we can do, but these are the most common ones. And so the first condition is independence. The counts are independent of each other, right? So the counts in each cell are independent of each other. I just realized that it could be confusing. I guess we're doing a test for independence, but the context is different, right? Here we're talking about the condition of independence of the counts, right? Whereas here we're talking about the independence between two variables, right? So the counts in each cell are independent of each other, which we can achieve by random sampling, or we have to assume that they're independent of each other. That can happen. And it happens quite often for chi-squared tests, but and then the sample size condition is that you have to have at least 5 expected counts in each cell. So each cell must have at least 5, an expected count of 5. Which means that before you do a chi-squared test, you need to find the expected counts before you can check the conditions, right? But then once you have, then it'll help you calculate your chi-squared test statistic. Okay. So for chi-square tests, right, we only do hypothesis testing. So I'm just gonna jump right in. Step one is to state the hypotheses. Now, I'm gonna use this one as a guide. And I guess I could do a nicer job of summarizing them. But the null hypothesis, and maybe I'll use dark. I want light blue to highlight the steps. The null hypothesis, if we want to be a little bit more clear, is that the variable 1 is independent of variable 2. Variable 1 is independent of variable 2. Right? Or if you want to, you can phrase it in the term of a relationship. There's no relationship between the two. They're independent of each other. And if you think back to when we were talking about independence in terms of probabilities, there's a link, but it's kind of far, it's like too far away for us. But now we're talking about, okay, in general, these two variables, are they just independent of each other, or is there some relationship in there? Right? It's not going to tell us what the relationship is, but it'll tell us if there's a relationship. So the alternative hypothesis is just the opposite, right? Variable 1 is not independent of variable 2. You can say dependent. I just like to use the negation instead. For me, it helps me think a little bit less. Think a little bit less, do a little bit more. So there is a relationship if you prefer to phrase it in terms of a relationship. Variable 1 and variable 2, it doesn't matter, right? So here in this table, I use this as variable 1 and this is variable 2. I could have flipped those. It doesn't actually matter, right? This could be variable 1 and this could be variable 2, right? As long as you just keep them separate. So then we've got our null and alternative hypotheses. Step 2, do the test. To do the test, we first need to find the expected values. So to do the test, so to calculate chi-squared, we need the expected counts for each cell, just like we did before. And I tell you that the expected count for each cell, ij, I is the row and j is the column, but that doesn't, it's not super important for us. So for each cell, you take the row total times by the column total and then divide by the grand total. Okay. So in terms of a kind of a, and maybe I'll use this kind of fake table, copy. So here, right, I can find the totals and the totals. So here's the column total 1, column total 2, column total, really wish I hadn't gone for 4 categories. Column total 3, column total 4. Then of course you have the grand total. Here we have row total 1, row total 2, and row total 3. I think I'm gonna need some lines, and hindsight's 2020. I shouldn't have made them all so squished. Right. The expected count for this cell is going to be the row total 1 times the column total 1 divided by the grand total. So you're always dividing by the grand total, but notice that as you move across row 1, the row total is not changing, but the column total is changing, right? Or could be changing. Sometimes we force the sample sizes to be the same, and that's totally fine, right? But the column total is changing, and then as you move down the rows, of course, the row total is changing, but the column total is staying the same, right? And so here, let's see here, because I need more space, the expected count, and I'm going to use 1, 1 for row 1, column 1, is row total 1 times the column total 1 divided by the grand total. To kind of mix things up here, what's a color I can use here? Right, if we do this expected in row 3, column 4, you don't have to use the subscripts. You can just do the expected counts in each one. In fact, often what I do is I'll kind of just calculate the expected counts in the same table that I'm given. Just kind of put them with the observed counts, because in my calculation, right, I need to do the observed minus the expected squared divided by the expected. So then if it's all there, then it's easier to see. But this would be the row total 3 times the column total 4 divided by the grand total. Okay. So for each cell, you're going to find an expected count, and that's what you're going to use to check your conditions, right? So you've probably already done this before getting to step 2, but then calculate chi-squared, which is the same as before, right? The formula just changed slightly because now you have rows and columns that you have to deal with. But if you want, you can totally ignore the subscripts, right? Observed minus the expected squared divided by the expected, and then add them all up, right? But you have to do all the cells. Okay. Then you have your test statistic, right? So your calculated chi-squared, you find it the same way. It's just now you have a bigger table to deal with. Okay. Then step 3, just one tiny new thing, right? How we find the degrees of freedom is going to change, but this is find the p-value. We have a chi-squared, so we can use the chi-squared table still, so that's nice. So we just know, okay, I need to find the degrees of freedom. How does that change? Oh, I would love to tell you. It's the number of rows minus 1 times the number of columns minus 1. Okay. So it's on your formula sheet. So let's see here. I'll use this table again, although it's kind of a hot mess now. There. So here, this is the number of rows. And this is the number of columns. Right, so for example, in our fake example, we had 3 and we had the number of columns is 4. So in this example, the degrees of freedom is 3 minus 1 times 4 minus 1. 2 times 3 is 6 degrees of freedom. Nice. Sometimes we can also write the degrees of freedom is R minus 1 times C minus 1. If you want to. I actually wrote it out on the formula sheet, right? So you'll have that, but sometimes you'll see R minus 1 and C minus 1. Now we're off to the races, right? Once I have a degrees of freedom, right? It doesn't matter how I got it. It doesn't matter how I got my chi-squared. Chi-squared stays the same, right? So then we use the chi-squared table as before. Right? Either using the p-value approach or the critical value approach, if that makes more sense to you. It's great. And you're welcome to use either approach on the quiz. Just make sure you use one of them. Okay. And then finally, step 4, the conclusion stays the same, right? If the p-value is less than the alpha level, that's always the conclusion, right? Then you have enough evidence to reject H naught. And so step 4, I won't even write it out here, is your conclusion, which same as always. So let's do an example. It's exercise 6.37. Exercise. Okay. Okay, yeah. I may as well just start this on a fresh page. All right. First glance, you don't even need to read the question, right? What should your gut reaction be? Oh, I see a two-way table. It has to be a test of independence. There's just no other way around it. You can confirm, right? Do I have 2 different variables that I want to test if they're independent of each other? Yes, I do, right? And so, so gut reaction for this quiz is, okay, if I have a two-way table, it has to be a test of independence, right? So the table below summarizes a data set we first encountered in blah, 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 that examines the responses of a random sample of college graduates and non-graduates on the topic of oil drilling. Complete a chi-squared test for these data to check whether there's a statistically significant difference in responses from college graduates and non-graduates. Okay. So this variable they labeled college grad yes or no, right? So we have a reference for this, but the support, oppose, and do not know, let's summarize that as just oil drilling, right? They either support it, they oppose it, or they don't know. And so let's just call this oil drilling. And we can call this variable college grad. Put little quotes around it. So feels like a lot of work just to start off with, right? But you can start with your null hypothesis, right? Get that out of the way. I'm gonna parking lot it for a little bit and just find the expected counts right away, because that's part of my condition, right? I have to have at least 5 expected counts in each cell before I can move on with my life. So first, find the expected counts for each cell. Okay. Kind of wish I hadn't, oh, maybe I can crop top this. Yeah, they kind of did totals for some, but not all of it. It's weird. Wait. So I have the totals, the column totals, but I don't have the row totals, and I do need that. So let's jot that down first. And I have them here, 286, 306, and 235. And the grand total is 827, right? And those need to add up across both the columns and the rows, because it's the same things, it's just across different variables. Okay, so now for my expected counts, I'm gonna recreate the table with the categories for each variable, right? But then I'm gonna show you the calculation for the expected counts. You don't need to show me your work for your expected counts, just because it can be kind of time consuming, right? And it's probably quicker to just do it. But I don't know, it doesn't hurt. Oops. So in terms of the support, oppose, and do not know. And then the college grad is either yes or no. Let's put the totals on here as well. Show off a little bit. Total. Okay. 286, 306, 235, 827. Oops. 438 and 389. Just like before, the totals, the expected totals should add to the actual totals, right? It's just redistributed. All right, so for the first cell, it's the row total, 286, times the column total, 438, divided by the grand total, 827. And I've got it here, and I hope there's no typos. 151.47, because I'm not going to redo it. And For the support of oil drilling, but no college degree, it's the row total again, 286 times the column total, which has changed 389 divided by the grand total 827, which is 134.53. Same deal, but moving on to the next row. So now my row total is changed. 306 times 438 divided by 827 is 162.07. Next one, 306 times 389 divided by 827 is 143.93. Finally, the do not know category, 235 times 438 divided by 827 is 124.46. And finally, 235 times 438 divided by 827 is 110.54. So what we want to know, right, with the chi-squared test of independence is, okay, are these values that we saw, are they significantly different from these expected counts, right? And we can look at them individually, but the chi-squared test does kind of a look in the box is, hey, is anything going on in here, right? And so 154 to 151, not a huge deal. 132 to 134, not a huge deal. 180 to 162, all of a sudden I'm feeling a little shaky, right? We need the spread in order to figure out if that's a big difference or not, right? So that's what the chi-squared test statistic does. Okay, so now with the expected counts, right, all of these are more than 5, so that's good. I'm ready to check the conditions. Right? And so the conditions, first is independence. Let's see if it says anything about examines the responses of a random sample of college graduates and non-graduates on the topic of oil drilling. So it was randomly selected, so we can assume that everyone in this sample, they're independent of each other, right? And so sample was randomly selected. So we may assume independence. Do you see how generic that statement is? You're welcome to just do something generic like that, okay? That way you can have it kind of a canned response, right? Which is nice. I'm gonna bump this down to new page here. Because I want the second condition, the sample size condition. All of the expected counts are greater than 5, right? So the sample size is large enough. All the expected counts are greater than 5. So the sample size is large enough. So that's good. Okay. Now we're ready to test this hypothesis, right? And if we go back to the question, right, we wanted to complete a chi-squared test for these data. So notice that they don't tell you what kind, right? But they do kind of nudge you towards a chi-squared test. For these data, to check whether there's a statistically significant difference in responses from college graduates and non-graduates. I'm going to rephrase that in terms of the null hypothesis on our formula sheet, which it just says that the variables are independent, right? And so then I'm going to say opinions on oil drilling and are independent of college grad. That doesn't sound good, but it works, right? Or maybe, let's see if I can come up with something snazzy. So now we're ready for the hypothesis test. So step 1 is to state the hypotheses. The null hypothesis is the variables are independent. That's what it says on our formula sheet. But I'm going to say opinions. That's something new. Opinions. Yikes. On oil drilling are independent or is independent of college graduation. The alternative is just the negation of that. Opinions on oil drilling are not independent of college graduation. Usually we say a degree, mention a degree, right? If someone has a degree or not, but I'll just keep the same variable name. Okay. I always think the null and alternative hypotheses are almost the hardest part, right? Because then once I have those, then I'm kind of, okay, now it's just calculations. But the wordings can be a little bit weird. Step 2, do the test. Do. The chi-squared is the sum of the observed minus the expected squared divided by the expected. Ditching all kinds of subscripts, but that's okay. So in our case, we had, let's see if I can grab these. We have our expected counts, copy. And we have our observed counts. Copy. Let's see. So then I'm going to write it out, and I have it kind of pre-baked Martha Stewart style. So we'll do that, but I'll write out the calculation. Oops. We don't need these totals anyways. Anymore. So chi-squared, the observed 154 minus the expected 151.47, then square it, then divide by the expected 151.47. So you have 154 minus 151.47, square it, divided by 151.47 plus. And I'll move across the rows, but it doesn't matter. 132 minus 134.53, then square it, divided by 134.53, plus next row 180 minus 162.07. Yes. Uh-huh.
235 times 438. Nope, the next one.
This one?
Yeah.
235. Oh. Okay. I have it correct in my notes. I just managed to screw that up. Thank you. 389. Gonna fix that here. Thank you. How easily you can muck things up. Plus 126 minus 143.93, square it, divided by 143.93, plus 104 minus 124.46, square it, divided by 124.46, plus finally 131 minus 110.54 squared, divided by 110.54. Phew. Chi-squared. And sometimes I put a little calculated here in case I need to remind myself, right, that this is the one I calculated, but I haven't really been doing that yet, but I think you can handle it. 11.4574678.5 is what I have in my notes. So I've calculated my test statistic. Step 3, find the p-value, or if you prefer, this would be find the critical value, right? Step 3, find the p-value or the critical value, right? You don't have to do both. They do the same thing. So first we need the degrees of freedom. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. You do not count the totals, of course. So we have the 3 rows and 2 columns. 3 minus 1 times 2 minus 1. 3 minus 1 is 2, and 2 minus 1 is 1. So then I get some very complicated math of 2. What? But it was such a big table. How can I only have 2 degrees of freedom? It just is. So that's why I say you really very rarely need anything more than 5 degrees of freedom. So now, okay, once you have your degrees of freedom, you're stuck on that line. Everything else you can ignore, right? 2 degrees of freedom. And we had a calculated value of 11.45 or 46 if we round to 2 decimal places. If you're using a table, you want to make it match the number of decimal places in the table, right? So if it has 2, you go to 2. If it has 3, you go to 3. Right. But this little guy, if I try to place it, how do I sneak it by here? We'll go somewhere in here. Okay. So what we can do is we can say that since the chi-squared calculated of 11 point, let's go to 46, 2 decimal places, is between 10.60 and 13.82, the p-value, remembering to read from right to left, is going to be between 0.001 and 0.005, very small. That's the p-value approach. I forgot the dash there. Or if you prefer to use the critical value, or let's see here, or the critical value approach, or I just want to give you both. We're going to assume that alpha is 0.05 because they didn't tell us what it was. So then 0.05, the chi-squared critical is 5.99. So since 11.46 is larger than the critical value of 5.99, we have enough evidence to reject H naught, right? So it's the same. So here, I'll just put the conclusion here because my formal conclusion, I'll use the p-value approach. It's what we're used to seeing. So since chi-squared calculated equal to 11.46 is greater than chi-squared critical equal to 5.99, we have enough evidence to reject H naught. In favor of HA. And I know I'm out of time. And that guy's gonna come in. But the conclusion, right, as step 4 is your conclusion. Let's see if I can pull it off. Since the p-value is between 0.001 and 0.005, it is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught, which means that opinions on oil drilling is not independent of college graduation. Done. I'll write that down before I post the notes, but I'll end it there. If you have any questions, let me know. Otherwise, I look forward to seeing you for the quiz tomorrow.
Awesome.